Hello friends, today we will read about the chemistry of lanthenoid elements from the modern publications. We have learned that the elements in which the last electron enters the f orbital of their atoms are called f block elements. In these elements, the last electron is added to third to outermost called anti-penultimate energy level, that is n-2f. These elements are called inner transition elements because these constitute transition series within transition series d block elements. They consist of two series of elements placed at the bottom of the periodic table. These two series are formed by the filling of electrons in 4f and 5f orbitals and are called lanthanoids and actinoids respectively. The series involving the filling of 4f orbitals following lanthanum La Z is equal to 57 is called lanthanoid series. The element present in the series are called lanthanoids. These are 14 elements in which series starting with cerium Z is equal to 58 and ending with lutetium Lu Z is equal to 71. The name lanthanoid is derived from lanthanum, the first member of the series. These lanthanoids are also sometimes referred to as lanthanones. All these elements have closely similar properties and therefore are considered together. The reason for their similar properties is that the 4f orbitals in which the electrons are added are embedded in the inner shells, while 5d and 6s electrons, which have similar configuration, are exposed more to the surroundings. Because of their similar physical properties, their separation and identification proved to be very difficult task. The first stage in their separation was to get them as oxides. However, the occurrence of the oxides of lanthanoids was very rare. Therefore, these elements have also been called rare earth elements. Nowadays, the term rare earth is not used. Their substantial deposits occur in Scandinavia, USA, USSR, and India. General characteristics of lanthanoids. The important general characteristics of lanthanoids are discussed below. First one is electronic structure and position in periodic table. The lanthanoid involves the gradual filling of 4f orbitals. It may be noted that the energy of d orbital and the next inner shell f orbitals 4f are closely similar, and therefore the order of filling the 4f orbital in the atom shows quite irregularities. At lanthanum, both 5d and 4f orbital become stable due to increased effective nuclear charge as a result of the poor shielding effect of 6s electrons. Therefore, it is observed that at lanthanum, the incoming electron enters the 5d orbital and its electronic configuration is xenon 5d16s2. However, as we move further after lanthanum, the energy of 4f subshell becomes lower than the 5d subshell, and therefore the next electron in cerium enter the 4f subshell. The filling of 4f orbital continues till we reach deuterium, in which the 4f subshell gets completely filled. It is clear from the figure that some deviations are observed in the regular increase order, such as for EU, ZD, YBLU. These are attributed to the stability of half-filled and completely filled F subshell. The first ionization energies are of the order of 560 kJ mole inverse, and second ionization energy of the order of 1150 kilojoule mole inverse. These values are quite comparable to alkaline earth metal, especially calcium. Melting and boiling points. Lanthanoids have fairly high melting and boiling points. However, the melting and boiling point do not show any regular trend as we move from La to Lu in the series. Inspections of table 4.2 shows the europium and ytterbium have unexpectedly low melting and boiling points. These atoms form Eu2 positive and Yb2 positive ions and result in weaker metallic bonding because there are less than 3 electrons per atom in metallic bond. The other lanthanoid atom gives 3 electrons per atom in the metallic bonds. Therefore, melting and boiling point of Eu and Yb are low as compared to values for The other lanthanoid element density, the density of lanthanoids are low, which range between 6.7 to 9.74 gram centimeter cube inverse. However, there is no definite trend in the density value of lanthanoid with increase in atomic number. EU and YB have unexpected low values. High heat of fusion and heat of vaporization. The heat of fusion and heat of vaporization also do not show definite trends with increase in atomic number. Electronegative values. The electronegative values of lanthanoids are quite close to those of alkali and alkaline earth metal. Therefore, lanthanoids are expected to form ionic compounds. Electropositive character. Because of low ionization energy and electronegativity value, the lanthanoids are electropositive like S block elements. Oxidation state. The common oxidation state of all lanthanoids is +3. In addition, some lanthanoids show +2 and +4 oxidation state. Also, these are shown by those elements which by doing so attain the stable F0, F7 and F14 configurations. Cerium and Tb exhibit +4 oxidation state. EU and YB exhibit +2 oxidation state. LAZD and LU exhibit only +3 states. F1, F2, F8 electronic configuration. The stability of these unusual oxidation state may be dependent upon some other thermodynamic and kinetic factor which are of significant importance, but these are less stable than the +3 state which is characteristic of this family. Color and spectral properties. The lanthanoids are silvery white, but many lanthanoid ions are colored but in solid state and in aqueous solution. The color remains same even on the change of anions. Therefore, the color are characteristic of lanthanoid ions. The color of ion depend upon the number of unpaired electrons because it has been observed that the ions containing NF electron have an almost similar color to those with 14 minus n bracket F electrons. The different ions having NF and 14 minus NF and their colors are given in table. However, it has been observed that some di and tetrapositive ions having same number of electrons as tripositive ions do not have same color. For example, Sm 2 positive and Eu 3 positive has same number of unpaired electrons but they have different colors. Some of other examples are given in the table like as Sm2 positive blood red, Eu2 positive straw yellow, Yb2 green, Cerium4 positive orange red. The color of lanthanoid ion arises due to absorption of light from the visible region of the spectrum, resulting in the electronic transition with the 4f level FF transition as a remarkable characteristic of the spectra of tripositive lanthanoid ion is that the absorption bands are extremely sharp line like bands in ultraviolet visible or near infrared regions. Many of these bands are line like and become even narrower as the temperature is lowered. This behavior is in contrast to absorption band of TD transition which have broad absorption band. The bands of lanthanoid are so sharp that they are useful for characterizing the lanthanoid ion. The main reason for very sharp absorption bending is that the 4f orbital lie deep in the atoms of these elements. Therefore, they are effectively shielded from the surrounding by the overlying 5s and 5p orbitals, and consequently, the absorption band arise mainly from the electronic transition within the 4f levels. Magnetic properties. All the lanthanoid ions with the exception of La3 positive, Lu3 positive, C4 positive and Yb2 positive ions are paramagnetic because they contain unpaired electron in their 4f subshell. The ions La3 positive, Lu3 positive, C4 positive and Yb2 positive which have 4f0 and 4f14 electronic configuration are diamagnetic because they have no unpaired electron. The magnetic properties of lanthanoid are different from those of transition elements. As we know, magnetic moments arises from two type of motion of electrons. The spin motion of electron around its own axis produce magnetic moment called spin magnetic moment, while the orbital motion of electron around the nucleus produces magnetic moment called called orbital magnetic moment. The observed magnetic moment of a substance is due to contribution of both the spin moment and the orbital moment. In the case of transition elements, the magnetic moment mainly corresponds to the spin only magnetic moment. This is due to the fact that the d orbitals are not well shielded from the environment and take part in the bond formation with the ligands. As a result, the d orbital the electron of metal interacts strongly with the ligands surrounding the metal ion. Due to the electric field of the ligands, the orbital motion of the electron gets restricted, and thereby the orbital moment of these electron get quenched. The magnetic moment of d block elements thus arises mainly from the contribution of spin motion of the electron only. The spin only magnetic moment is given as mu spin only is equal to under root of n bracket n plus 2 bracket close. Here n is the number of unpaired electrons. This relationship gives almost correct values of magnetic moment for d block elements. However, the above relationship is not valid in the case of f block elements. In these elements, the 4f orbitals are well shielded from the surrounding by the overlying 5s and 5p subshells. As a result, the electric field of ligand surrounding the metal ion does not restrict the orbital motion of the electron. Thus, orbital contribution contribution is not quenched. Therefore, the magnetic moment of lanthanoid ion is due to both electron spin and orbital motion of electron. This may be calculated from the relation mu is equal to under root of 4s bracket s plus 1 bracket close plus l bracket l plus 1 bracket close, where s is the resultant spin quantum number, l is the resultant orbital momentum quantum number. The theoretically and experimentally observed magnetic moment values are given in the table. For table 6, the magnetic moments of lanthanoid depend upon the atomic number and the number of unpaired electron. Ionic radii lanthanoid contraction. We know that as we move down a group, atomic sizes covalent or ionic radii normally increases. This is mainly due to additional shells or electron between the successive period. However, as we move across a period from left to right, atomic sizes decreases. This is attributed to the increasing effective nuclear charge, as a result of which the outermost shell of electron is attracted more and more. Consequently, the size decreases. If we consider the ionic radii of lanthanoids, we get very interesting observation. For comparison's sake, we can take the ionic radii of trivalent ion M3 positive, which are most stable. It is clear that ionic radii decrease from one element to another is in the lanthanoid series, but decreases is very small. It has been observed that cerium to Lu3, the ionic radii decreases from 1.03 angstrom to 0.86 angstrom. Obviously, from an increase of atomic number 14, the decrease in ionic radii is only 0.70 angstrom. This is very small decrease in comparison to elements of other group and periods. Similarly, on moving from cerium to lutetium, the atomic radii from decrease from 1.65 angstrom to 1.56 angstrom, and the decrease is only 0.09 angstrom. This small steady decrease in ionic or atomic sizes of lanthanoid element with increase in atomic number is called the lanthanoid contraction. Cause of lanthanoid contraction. In lanthanoid series, the 4f electrons are being added one at each step. As we move from one element to another, the shielding of one f electron by another from the nuclear attraction is quite weak due to the shapes of the f orbitals. The nuclear charge, however, increase by one at each step. Hence, the increasing atomic number and nuclear charge, the effective nuclear charge experienced by each 4f electron increases. Hence, the inward pull experienced by the 4f electron increases, and this causes a reduction in the size of the atom or ion. The sum of the successive reduction gives the total lanthanoid contraction. Consequences of lanthanoid contraction. Lanthanoid contraction has very significant effect on the relative properties of elements which precede and which follow the lanthanoids in the periodic table. Some important consequences of lanthanoid contraction are given below. Steady decrease in size. There is regular decrease in the ionic radii of lanthanoid. Electronegativity. There is slight regular increase in the electronegativity of the trivalent ions. Electrode potential values. There is small but smooth increase in standard electrode potential values for the process. M3 positive plus 3 electron gives M. For lanthanum minus 2.52 V2 minus 2.25 volt for lutetium. Resemblance of second and third transition series. The lanthanoid contraction affects the chemistry of second and third transition series. As we can see from table 8, there is a regular increase in size from scandium to yttrium to La. Similarly, we expect normal increase in size in other groups. However, after lanthanoid, the increase in radii from second to third transition series almost vanishes. The pairs of element zirconium, hafnium, NBTA, MOW possesses almost the same size. The properties of these elements are very similar. Similarity among lanthanoids. Because of the very small change in the size of lanthanoid ion in lanthanoid, their chemical properties are similar, therefore their separation become very difficult. Recently, methods based on repeated fractional crystallization or ion exchange techniques which take the advantage of slight difference in their properties arising from very slight size differences of their trivalent ion have been used. Basicity differences. Due to lanthanoid contraction, the size of lanthanoid ion decreases regularly with increase in atomic number. As a result of decrease in size, their covalent character between Ln3 positive ions and OH negative ions increases, and therefore the basic strength of the hydroxide decreases. With increase in atomic number, thus LaOH3 is the most basic while LuOH3 is least basic. The basicity differences in lanthanoids are reflected in A. Increases tendency to get hydrolyzed due to decrease in basic character. There is a slight increase in degree of hydrolysis in solution from La3 positive to Lu3 positive. Example, La3 positive ions are less radially hydrolyzed than Lu3 positive ions. Thermal decomposition of oxysalts. More basic oxysalts decompose less radially. Example, LaNO3 bracket close 3 decomposes with difficulty and is stable, whereas LuNO3 bracket close 3 is unstable and decomposes radially. Solubility of salts. Lanthanoid hydroxide precipitate at regularly decreasing pH values from La3 positive to Lu3 positive. Example, LaOH3 at 7.83, ZdOH3 at 6.83 and Lu3 positive at 6.30, all from nitrite solution at 20 degrees Celsius. Sizes of YbHO and dy. Due to lanthanoid contraction, the radii of Yb3 positive is comparable to have heavier lanthanoid Tb, Dy, Ho and Er. Therefore, they occur together in natural minerals. Reactivity of lanthanoid. All the lanthanoids are highly electropositive metals and have almost similar chemical reactivity. This is due to the fact that the lanthanoid differ only in number of 4f electrons. Since these electrons are very effectively shielded from interaction with other elements by the overlying 5s, 5p and 6s electrons, they show very little differences in their chemical reactivity. Because of their similar chemical reactivities, their separation from one another is very difficult. The lanthanoids are in general more reactive than d block elements. Some of their chemical characteristics are they tarnish radially on exposure to air in finely divided state, all burn in air to form of the formula Ln2O3, where Ln stand for lanthanoid, except cerium, which gives CO2. Ytterbium, however, resists the action of air even at 1000 degrees Celsius due to formation of a protective coating of its oxide. All react with water slowly in cold but rapidly on heating, liberating hydrogen and forming LnOH3. All these combine with hydrogen at 200 to 300 degrees Celsius, giving LnH3. They also combine with halogens, oxygen and sulfur. They act as a strong reducing agents for oxides of the other metals. Cerium is used as a squenger of oxygen and sulfur in many metals. They react with nitrogen to form nitrides of the formula LnN. Solubility of compound. The fluorides, oxides, hydroxides, carbonates, phosphates, chromates, and oxalates of lanthanoids are largely insoluble in water. On the other hand, the halide other than fluorides, nitrites, acetates, perchlorates, and salts of oxoacids of lanthanoids are soluble in water. The solubility behavior of salt and of lanthanoids follows the pattern of solubility of salts of group second elements. However, lanthanoid sulfate, unlike the sulfate of group second elements, are soluble in water, tendency to form complexes. Although the lanthanoid ions have a high charge +3, yet they have large size of their ions compared with the transition metals. As a result, they have low charge density and therefore they have very less tendency to form complexes. Their complexes with unidi unidentate ligands are very few and form complexes only with fluorine and oxygen donor ligands. However, they form complexes with a few chelating ligands such as beta diketones, oximes, and ethyl diamine, tartaric acetic acid, alpha alpha dipyridyl, and hydroxycarboxylic acid such as citric acid. These complexes usually have a high and variable coordination number, and water or solvent molecules are often attached to the central atom. Beta diketone complexes of EU3 positive and PR3 positive dissolved in organic solvent are used as lanthanoid shift reagents in NMR spectroscopy. In contrast to transition elements, the coordination number 6 is not very common. Coordination number below 6 is also uncommon and occur only with bulky ligands such as 2,6-dimethylphenyl and NSIMe32 ligands. However, coordination number 7, 8, 9 are common, and these give a variety of stereochemistry and thought to be 9 for nearly lanthanoid and 8 for the later smaller members of the series. However, these ions are highly liable. The smaller ytterbium ion Yb3 forms 7 coordinated complex YbACAC3OH2, and the larger La3 is 8 coordinated in LaACAC3OH2, where ACAC is acetyl acetonate. The structures of these complexes are a capped trigonal prism and a square antiprism as shown below in figure 4. Coordination numbers 10 and 12 occurs with the larger lanthanoid and small chelating ligands such as NO3 negative and SO4 2 negative. CE4 is smaller and highly charged and forms CeNO3 6 2 negative in the non-aqueous solvent N2O4. When two trans nitrates of this complex are replaced by PH3PO, it gives the 10 coordinated orange colored neutral complex CeNO34OP PH32 as shown in figure 6. The sulfates CeSO4 and CeSO4 2 negative and H2O N is equal to 0, 4, 8 and 12, and NH4 2 CeSO4 3, and the iodates are also known. Large number of salts of organic acids such as oxalic, citric, tartaric have been studied mainly for separation methods. These anions have chelating O ligands forming complexes with Ln3 unidentate O donor such as pyridine N oxide and triphenyl phosphine oxide. Also from many complexes with lanthanoids in +3 oxidation state. Complexes with ligands such as E and diene, bipi, tripi can also be prepared in polar organic solvents. As with other transition metals, the lanthanoid can induce to form complexes with exceptionally low coordination numbers by use of bulky ligands such as NSIMe32 negative. This is an example of coordination number 3, which is the lowest found for lanthanoid. They are volatile, air sensitive, and easily hydrolyzed. They are planar in solution but pyramidal in the solid state with pH3PO. The four coordinated distorted tetrahedral adducts are formed. Lanthanoid also form two main types of organometallic compound, predominantly ionic cyclopentadienydes and alpha bonded alkyls and aryls. These type of compounds are usually thermally stable but unstable with respect to water and air. In polar solvents, these complexes are solvated and are monomeric, but in non-polar solvents, the tris C5H5 compounds are insoluble while the bis C5H5 compound dimerizes. The lanthanoids also form alkyls and aryls by metathesis in THF or other solutions. Double salt formation. The lanthanoid salts form double salt with corresponding salt of ammonium and alkali metals. Example NH42SO4 dot Ln2SO4 3 8H2O. Double salt like alum with 24 water molecules are formed. This is because the lanthanoid ions are so large that these cannot coordinate to 24 water molecules octahedrally as in alums. Occurrence of lanthanoids. Although lanthanoids were originally called rare elements, the recent studies have shown that these are not rare. All the lanthanoids except promethium occur naturally. Some of them, particularly cerium, lanthanum, neodymium, are very common and occur in fairly large quantities. Cerium is the 26th most abundant of all the elements. It has been observed that lanthanoids having even atomic number are more abundant than their neighbors with odd atomic number. Methods for separation into individual elements. The properties of metal ions are determined by their size and charge. All the lanthanoid ions are trivalent, carry same charge and have almost same size so that their properties are almost identical. Therefore, the separation of lanthanoid from one another is very difficult. Recently, methods based on repeated for fractional crystallization, ion exchange techniques, etc., which take advantage of slight differences of properties like solubility, complex ion formation, and hydration arising from very slight size differences of their trivalent ions have been used. These methods are discussed below. Repeated fractional crystallization. Simple salt of lanthanoids such as nitrates, sulfates, bromates, oxalates as well as double salts form well-defined crystals. The solubilities of these salts decrease from La to Lu and therefore by repeating fractional crystallization a number of times the individual components can be obtained during fractional crystallization. The less soluble salt will be obtained first and the most soluble salt will be obtained last of all. By repeating the crystallization process, the less soluble salt will be accumulated more and more in the crystals and the mother liquor will contain more and more of most soluble salt. This method has now been improved by the use of non-aqueous solvents such as ether. Fractional precipitation. When only a small amount of precipitating agent is added to a mixture of lanthanoid salts, the substance having the lowest solubility product will be precipitate most rapidly and most completely. For example, if sodium hydroxide is added to a solution of lanthanoid, lan, lanide nitrates LuOH3, which is the weakest base and has the lowest solubility product, is precipitated first, while LaOH3, which has the highest solubility product, is precipitated first. A partial separation takes place in the manner by redissolving the precipitates and then precipitating again a number of times. It is possible to have complete separation. Solvent extraction. The partition coefficients of the salt of these metals between water and organic solvents are slightly different. Therefore, these can be extracted by using different solvents and repeating the extraction process again and again. For example, the partition coefficient of ZdNO3 3 between water and normal butyl alcohol is 1.06 times greater than that of LaNO3 bracket close 3. This means that GdNO3 can be separated from LaNO3 by continuous extraction with water from a solution of this salt in butyl alcohol. Change of oxidation state. Some of lanthanoids show plus 4 and plus 4 oxidation states in addition to the plus 3 state, which is most characteristic of all the lanthanoid. The properties of the M2 positive and M4 positive ions are different from those of usual M3 positive ion. For example, cerium can be separated from a mixture of trivalent ions of all the lanthanoid by oxidizing it to cerium 4 positive state by reacting it with alkaline KMnO4. Cerium 4 positive ion has a greater charge than Ce3 positive ion, therefore it is smaller and less basic and less soluble. It can be precipitated as CaOH4 by the addition of a small amount of an alkali, leaving all the trivalent lanthanoid ion in solution. Similarly, europium can be separated from a mixture of trivalent lanthanoid ion by reducing it first to the plus 2 state by zinc amalgam. Then Eu2 positive can precipitate it as EuSO4, which is insoluble in water. The sulfate of the trivalent lanthanoids, on the other hand, are soluble in water and remain in solution. Thermal decomposition. When a mixture of lanthanoid nitrate is fused along with the some alkali metal nitrites, a temperature is reached when the less basic nitrite changes to oxide. Therefore, heavier nitrite decompose first, while light lanthanoid nitrite decompose last of all. Therefore, the process of decomposition of nitrites at different temperature is carried out, and the oxides separated at each stage are then dissolved in HNO3. There are about 100 minerals known to contain lanthanoids. The main minerals are monazoid, monazite. It is the most abundant and most widespread mineral and account for about 78% of the lanthanoids mined. It is a mixture It is a mixture containing La phosphate and trivalent phosphate of the lighter elements such as C, Pr, and D. It also contains small amount of heavier element and thorium phosphate. This mineral is contaminated with other similarly concentrated minerals such as ilmenite, FeTiO3, and cassiterite, SnO2. Monazite occur in southern India, South Africa, Brazil, Australia, Malaysia, etc. Bastanacetite. It is a mixed fluorocarbonate M3CO3F where M is a La or lanthanoid. The distribution of the metal in monazite as bastanacite is almost similarly mainly cerium, La, Nd, and Pr, but the difference is that monazite contains around 5 to 10% THO2 and 3% Yttrium heavier lanthanoid earth, which are virtually absent in bastanacite. A large amount of bastanacite minerals are found in California, Sweden, New Mexico. Cerite. It contains silicates of CeLaPr, Nd, and Sm. It is found in Norway and Sweden. In addition to above three main minerals, many of other minerals in small amount are euxenite containing Ce and Th ytterbium earths, certhite containing double silicates of cerium, xenotime containing ytterbium and Th, gadolinite containing ytterbium earths, Cth. Isolation of lanthanoid. Monazite is the best known mineral containing of lanthanoids. It is a mixture of phosphate LnPO4 where Ln stand for lanthanoid element containing thorium, zirconium ion, and titanium as silicates. The mineral is powdered and digested with hot concentrated H2SO4 until a paste is obtained in which the phosphate changes into corresponding sulfate. The paste is separated by centrifugation and treated with cold water. The sulfates, being more soluble in cold water than in hot water, pass into the solution, while silica, SiO2, zircon, Zr, SiO4, etc., being insoluble, are removed.
The solution is neutralized with NH4OH when thorium, zirconium, and titanium are precipitated out as phosphates. Then the solution is treated with sodium sulfate, which precipitates out La and light lanthanoids as double salts, while the heavy lanthanoids still remain in the solution. The precipitated double salts of light lanthanoids are treated with hot sodium hydroxide solution when they are converted into a mixture of oxides and hydroxides. The mixture is washed to remove sodium sulfate formed during the process and dried in air at 100 degrees Celsius. In this process, cerium is completely oxidized to CO2 and the other lanthanoids are changed as oxides. The mixture has approximate composition as CEO2 50, Nd2O3 20, La2O3 17, Pr2O3 8, Sm2O3 5. The mixture is treated with dilute HNO3 so that all lanthanoid oxide except CO2 dissolve. The CEO2 is left as residue and is filtered. The crude CO2 is dissolved in 85% HNO3 and added to an excess of dilute H2SO4 whereby the cerium is precipitated as red basic nitrate COH NO3 bracket close 3.3H2O. After the removal of Ce, the other light lanthanoid are separated into individual components by different methods based mainly on solubility differences. Ion exchange method. This is the most successful and the most efficient method for the separation of lanthanoids. Generally, a column of synthetic ion exchange resin with acid functional groups such as COOH or SO3H is used. The solution containing the trivalent lanthanoid ions is passed through this column and the hydrogen ions are replaced by the metal cations. The ions which are bound least firmly to resin are displaced by the ammonium ions first, while those which are bound most firmly are displaced last. The firmness with which lanthanoid ions are fixed to the resin depend upon the size. That is, the smaller the size of lanthanoid ion, the more firmly it is bound to the resin and vice versa. Since lanthanoid ions are present as hydrates, the firmness depends upon the size of hydrated ion. Smaller ion is hydrated to greater extent, therefore the smallest lanthanoid ion will be most heavily hydrated, while La3 positive ion being largest will be hydrated to minimum extent. Hence the size of hydrated La3 positive ion is the smallest and therefore it is attached to column with maximum firmness. On the other hand, Lu3 positive ion is attached with minimum firmness and the firmness decreases from La3 positive to Lu3 positive. Thus, Lu3 positive ion is eluted first while the La3 positive ion is eluted last. By complex formation, lanthanoid oxalates are insoluble in water but they can dissolve by complexing with ethyl tetraacetic acid. These complexes differ in their stabilities towards acid. The least stable complex is destroyed first and changes to the oxalate, while the most stable complex is destroyed last. On the addition of an acid, production of metals. The lanthanoid metal can be produced by the following methods. Electrolysis of the fused chlorides. The method is similar to that used for the preparation of calcium by electrolysis of calcium chloride. Electrolysis of CO2 infused CF2. This method is used in the production of cerium and is similar to the method used in metallurgy of aluminium. Reduction of anhydrous chloride with sodium. The reduction takes place at high temperature above 1000 degrees Celsius. The method is used for the production of lighter lanthanoid such as LaCe and Ze. Reduction of anhydrous fluoride with calcium or magnesium. This method used in the production of heavier lanthanoids because their anhydrous fluorides are non-hygroscopic and less volatile than the chloride. The loss by evaporation is therefore small when fluoride are used instead of chlorides. The reduction is carried out at temperature above 1000 degrees Celsius. Uses of lanthanoids. The pure metal have no specific uses and therefore these metals are extracted as mixture of alloys. These are called miscible metals. The common uses of lanthanoids and their salts are given below. Cerium constitutes about 30 to 50% percent of the alloys of lanthanoid. They are used for squeezing oxygen and sulfur from other metals. Addition of about 3% misses metal to magnesium increases its strength and is used in making jet engine parts. Steel mixed with LaCePr and Nd is used in the manufacture of flame throwing tanks. Lanthanoid oxides are used for polishing glass. Neodymium and paraceodymium oxides are used for making colored glasses for goggles. These are particularly useful for glass blowers as they absorb the bright yellow light. Cerium salts are used in dyeing cotton. They are also used as catalysts. Lanthanoid compounds are used as catalyst for hydrogenation, dehydrogenation, oxidation, and petroleum cracking. They are also used in magnetic and electronic devices for their paramagnetic and ferromagnetic properties. Gadolinium sulfate heptahydrate has been used to produce very low temperature. Recently, lanthanoids have been used in lasers. For example, neodymium oxide dissolved in selenium oxychloride has been used as a powerful liquid laser. Cerium magnesium alloys are used in flashlight powders. Thank